Section 12.9 deals with really the very last part of our infinite series chapter. There are actually two other sections after this, and then we wrap it all up. But we really shift gears in this section, focusing specifically on functions and how they relate to infinite series, and in fact power series. Power series is what we studied in section 12.8. So I've highlighted here really something that I hope is familiar from the geometric series. In the geometric series, of course, what we have studied even last year in pre-calculus is that if you had a geometric series and if your common ratio was less than 1 in absolute value, then of course we would have that series converge. We'd have this add up to a sub 1, the first term, divided by 1 minus your common ratio. Our first term in this regard would be a 1. Our common ratio is just called r, so we'd have 1 all over 1 minus r. Usually kids feel pretty confident with that. They feel okay with it. In a power series, our r has been replaced with x. But I guess what I really want us to think about is this, that 1 all over 1 minus x could be thought of the function 1 divided by 1 minus x. In other words, that function, which you have graphed in the past, you've probably tried to find vertical asymptotes for, find domain, range, and all that good stuff. We could say, do you know what, this function could be written as an infinite series when x is less than 1 in absolute value. So that's what we're going to be doing today. We're going to be looking at functions, and we're going to work a lot off of this very famous geometric series. Now, take a look at example 1. It's going to look ever so slightly from what we've just talked about. Your common ratio is no longer x in this regard. It would be opposite x. So find a function represented by this series. Well, if I may, though, maybe help you out going in a different direction. If we just recopied this above statement, and everywhere where we had an x, if we just left that as a blank, I hope we could see that if we wanted to, we could be very clever and substitute in an opposite of x. We'd like to be able to see what's happening here. Imagine what's happening as every place where we see a little space here, we were replacing that with opposite x. Now, not only is this going to hold true for all the way up to our general nth term, which by the way would be right over here, -1 to the n, and here we'd have a blank to the n. We could very quickly see what exactly is happening. We would arrive at the function 1 all over 1 plus x equals 1 minus x. Every time we raise opposite x to an even power, of course that even power is going to go away. So look at this. We have come up with a way to represent this series that they were asking us to find. And very nicely we can see that it's 1 over 1 plus x. So my goodness, we actually have a wonderful way to deal with this. Now, in the past we saw that absolute value of x is less than 1, but look, even if we had the opposite value of x, if we were to replace, imagine here's the absolute value of x as a space here. If we put opposite x in there, it would still just, the absolute value of a negative just changes to a positive. So my goodness, this other series right here, 1 over 1 plus x. Yes, it's still a geometric series where your common ratio is actually opposite x. But what we're going to see, my goodness, is we will use that equally as much. We're going to use it quite a bit. By the way, one other little thing, we could say that this previous statement is going to arrive at a sigma just as well. We'd say that it goes from n equals 0 to infinity still. We're still going to have x to the n, but imagine that even up here in our sigma, if we plugged in an opposite x, that's -1 raised to the n, just as we've done in some of these power series. You'd see it's an alternating series. Okay, let's take a look at example 2. Express 1 over 1 minus x squared is the sum of a power series. Well, if I may, let's immediately take a look at the very first, in yellow, statement that we had up in here. We had 1 all over 1 minus x was equal to 1 plus x squared plus x cubed. We said that this could even arrive at a sigma. We could say that this was from n equals 0, x to the n, and this was for the absolute value of x less than 1. We're going to do this so much in this last part of our study of series. We're going to say, wow, what if we could go to a series that we already have worked out? What if we would just make a very simple substitution in there? Wherever we see an x, we could replace it with something else. And again, I'm going back to this spacing. We're going to use this so very frequently, and the quicker we get used to this, the better off we're going to be. So even right here in sigma, we can imagine that that's a blank. We could say now we've got the absolute value of this blank less than 1. Well, see, look what we're looking for. We really want to see x squared get put into that space. So very quickly, everywhere where we see a space, it's putting in an x squared. This is x squared quantity squared. Here's x squared cubed. Kids will quickly notice that even in sigma, and especially in sigma here, if you had x squared to the n in your sigma, we'll deal with that in just a moment. We're going to say, well, wait a minute, what if we replaced x squared in that little space there? What is this series really going to look like? Well, 1 plus x squared plus x to the 4th. You can see that this next term, 2 times 3 is 6. We have all even powers. By the way, our sigma certainly would have led us to believe that we have even powers. X to the 2n. Now, by the way, x squared less than 1, we've talked about this for some of the power series also. Technically, this would lead us to x squared less than 1. X squared's non-negative. We don't even need to keep it in absolute value. This will go for x between -1 and +1, we have seen. That's actually even equivalent to writing that the absolute value of x is less than 1. So look, we've actually arranged a new series. We're seeing that 1 all over 1 minus x squared could be written in this way. Again, what are we really saying? This series is representing the function. Take a look at example 3. If I may, I'm going to look at 1 over x plus 2 is 1 all over 2 plus x. And after that, I'd like to actually factor out a 2. Now, very often kids might say, why are you doing that? Well, here's why. Let's do a little bit of work over here. I'm going to say recall the formula where we have 1 plus x in the denominator. Look up above. In example 1, we derived such a formula. It's coming straight from this geometric series. This is where it's an alternating series, of course. And in regards to sigma, we could say this is n equals 0 to infinity, -1 to the n of x to the n, and this would be converging for absolute value of x less than 1. So sometimes kids look at this and they'll say, well, how should I use this? Well, again, take a look at this series that I've just deliberately recopied, and everywhere where we see an x, we can envision that there's a little space there. And you know what? We don't see an x in this regard. We're going to see x all over 2. So notice what we're about to do. We've got this 2 factored out down below, and we're going to deal with that in just a second. But tell you what, I'm going to rewrite this step by step. I'm going to say this is 1 plus x all over 2. This is 1 minus x all over 2 plus x over 2 squared plus x over 2 cubed, or I should say minus, pardon me, minus x all over 2 cubed. And just continuing into sigma, notice even here in sigma, this substitution of x all over 2 comes into play. So even in this absolute value, I am replacing x with x all over 2. Well, what would this really simplify into? Well, I think you can see quickly it's x squared all over 4 minus x cubed all over 8. And look inside of sigma. I think this could be especially helpful. You'll see that you've got -1 to the n, x to the n divided by 2 to the n. And this is going to be for the absolute value of x less than 2. I could multiply both sides by 2. Now, notice what's about to happen. If I were to bring this 2 down here, I'm going to have to really divide every term by 2, or multiply every term by a half. So if I were to plug that extra 2 back in here, how have I just changed the formula from the step above? Well, I've multiplied by a half. That means multiply every term here by a half as well. Every individual term. And oh, is that important? We're going to talk about how individual term by term, is affected. We're going to see that even in just a moment. So what's this series really going to look like? Well, down below we'll have 2 to the n plus 1. This obviously has not affected x. We're still going to be convergent in absolute value for x less than 2. But this is what 1 over 2 plus x, that function, will converge to this power series for x values in absolute value less than 2. Alright, let's take a look at this green box or gray box real quickly, and hopefully just glance at it and do some examples in just a minute. Suppose we have a power series with a radius of convergence r greater than 0. And we've talked about that before. This would be your r is always going to be, as you solve for the absolute value of x, this is r, your radius of convergence. So notice that we're starting at 0, and of course, just as I said, if r is your radius of convergence, you're between opposite r and r. When we take a derivative, we can take a derivative term by term, and that constant term in the beginning, a sub 0, drops out. Notice our new sigma would go from n equals 1 to infinity. We could even look at this as an nth term. Bring down the n times a sub n, x to the n minus 1. Wow. We could also integrate from 0 to x, integrating term by term. Notice here, sigma would still begin at 0. We're going to continue talking about this. Hopefully this is making some sense. We'll continue in a moment.